Learn like a pro.
All right, today we are going to pop the hood on reality itself. Seriously, we're going to build a kind of physics engine right from the ground up, and we'll see exactly how the universe takes this jumble of pushes and pulls and turns it into the smooth, predictable motion we see everywhere.
I mean, just think about it for a second. Everything around you, from a ball rolling down a hill to a planet orbiting the sun, is constantly being pushed and pulled by all sorts of forces. So how does any of it make sense? How do we get predictable movement out of all that chaos? Well, that is the big question we're going to answer today.
So here's our game plan for building this engine. First up, we've got to understand the most basic part, what a force even is. Then, we'll see how to combine them all together. After that, we'll plug in the main brain of the operation, Newton's second law. And to wrap it all up, we're going to run a few diagnostics with some real-world examples.
Okay, time to get started. The absolute most fundamental building block of our whole physics engine is the idea of a force. But what does that really mean?
Now this is super important. You gotta get this. A force isn't just a number. It's what we call a vector. That means it has two critical pieces of information. Its magnitude, that's just how strong it is, which we measure in newtons, and its direction. You know, pushing a box with 10 newtons of force to the right is totally different than pushing it upwards with that same 10 newtons. Both pieces of the puzzle matter. A lot.
So, we have our basic components, our forces. But, in the real world, things almost never have just one single force acting on them. We need a way to add up all these different pushes and pulls to figure out what's actually going to happen in the end.
And that's exactly where this idea of the resultant force comes into play. You can think of it as the single overall force that's left after you've tallied up everything else. It's the final net instruction that tells an object, okay, here's how you're going to move now. And the great thing is, we already get this intuitively. I mean, if you and your friend are both pushing a car in the same direction, you're obviously helping each other out. Your forces add up to create one bigger, stronger push. It sounds simple, but it's a huge piece of how all this works.
On the other hand, what happens in a game of tug-of-war? Well, this is it right here. When forces are pulling in opposite directions, they fight against each other. They can weaken each other, or if they're perfectly matched, they can cancel each other out completely. It's this constant battle between opposing forces.
Okay, so this whole idea of a single resultant force, that is the key that lets us install the next part of our engine, the central processor. This is the thing that actually connects force to motion.
We've seen what happens when forces are perfectly balanced, right? They cancel out. But what if they aren't? What happens when one side of the tug-of-war actually wins? That's when things get really dynamic.
And here's the answer laid out perfectly for us. If that resultant force adds up to 0, then there's no change in motion. The object's in what we call equilibrium. But if there's any leftover force, any non-zero resultant force, that's when you get acceleration. That's when things start to speed up or slow down.
And this entire relationship, this core rule of the universe, is captured in one of the most elegant and powerful equations ever written. F equals ma. The resultant force on an object is equal to its mass times its acceleration. This is it. This is the heart of our physics engine.
And it's so important to understand how these pieces relate to each other. It's pretty straightforward, really. The more force you apply, the more acceleration you're going to get. But, and this is the flip side, the more mass an object has, the less it's going to accelerate for that same amount of force. It's this beautiful balance.
Okay, our physics engine is officially assembled. So now let's fire this thing up and run it through a few tests to see how it handles some real-world situations. All right, let's start with a classic. We're pushing a 5-kilogram box, we're applying 20 newtons of force, but we've got 12 newtons of friction working against us. So what's the first step? We find the resultant force. 20 minus 12 gives us 8 newtons. Then we just plug that into F equals ma, and we find our acceleration is 1.6 meters per second squared. Simple as that. Okay, next up, let's take this to the track. We've got a car that weighs 2,000 kilograms, and its engine is providing a resultant force of 3,000 newtons. Pop those numbers into F equals ma, and boom, we can figure out that the car will accelerate at 1.5 meters per second squared.
Now, this last one is a fantastic way to really see that relationship between mass and acceleration. See, the truck's engine is putting out the same force in both cases. But when you load it up with cargo, you increase its mass. And what happens? The acceleration drops. It's that inverse relationship in action. More stuff means it's harder to get moving.
And there you have it. This flowchart right here, this is basically the complete blueprint for our engine. You figure out all the forces, find the resultant, and that tells you exactly how the object is going to accelerate. It's a logical pathway that works for anything, anywhere in the universe.
So, we've seen how this one simple rule, F equals ma, can predict the motion of a box, a car, a truck, pretty much anything. But that brings up a really cool question, doesn't it? If this one law is so powerful, how does it scale up to explain something as incredibly complex as launching a massive rocket into space? Well, that's a story for another time.